Video, you're watching lesson 5 on mix and flow of matter. This lesson will focus on buoyancy and what that word means and how it can be applied. So, buoyancy is the tendency for something to float. Buoyancy, you need to know this word, buoyancy, is the tendency for something to float in a fluid. Now, when I say fluid, I don't just mean water or liquid. If you remember from grade 7, a fluid can be a liquid, right? A liquid, or a gas. And that's because fluids are anything that can flow. Liquids flow, gases flow. But we'll talk about that later. All buoyancy is if something floats, we call it buoyant, right? And if something sinks, we don't say it's buoyant. Well, what makes something float? What gives something buoyancy? What gives something the tendency to float in a fluid? Well, buoyancy can be determined by its buoyant force. Buoyant force, you need to know this. This is the upward force objects feel when in a fluid. It is the upward force objects feel when in a fluid, and its density. And its density, which is how much matter is in a given space. And if you remember, density can be calculated, probably have too small of a triangle, but density can be calculated via this triangle. You have, M here over V and D, right? If you want to find the density, it's mass divided by volume, which gives you density. So density is how much stuff or matter is in a given space, and buoyant force is the upward force an object feels when in a fluid. So when you put an object in a liquid or a fluid, the gravity of the planet will pull down on the object, while the buoyant force will push up. And so if the buoyant force is greater than gravity, the object's going to float because the buoyant force, the up force, is larger than the down force. Pretty simple, right? If something sinks, the gravitational force is greater than the buoyant force, the upward force. And so gravity is going to push it down, albeit more slower than if it wasn't in a fluid, but it will still push it down or pull it down. As an object is put in a fluid, it moves the fluid away. As you put an object in a fluid, the object will push the fluid away from it. And so the fluid here, as we put this object in the liquid, or as it falls due to gravity, the fluid will be pushed away. However, the fluid pushes back, and that creates the buoyant force. So the buoyant force is the upward force, and that's created by the fluid being pushed away. Because it doesn't want to be pushed away. It doesn't want to be moved out of the space that it was in, right? This object has now suddenly moved in and is taking up all this space. Well, now the liquid, or the fluid, wants to push it back out. And that pushing out force is our buoyant force, the upward force. So let's take a look at a classic example. A tinfoil boat will float, but a tinfoil ball will sink. This is true even when there's the same amount of foil, the same amount of tin in both. So we look at this ball at the bottom, and we look at the boat. They both have the exact same amount. If you weighed the boat, it would have the same mass as the tin. So let's say they both weigh 10 grams. Let's just say they both weigh 10 grams. Okay, they both weigh 10 grams, but for some reason, the boat's gonna float, but the ball's gonna sink. Well, they're both the same amount of material, so what gives? Well, essentially, it's because even though they both weigh the same, they have the same mass, the ball is more dense. Again, density is how much matter is in a space, right? So yeah, it's the same amount of matter, but the ball takes up less space. So there's more matter in a smaller space. So it's more dense. While a boat, or this boat, has the same amount of material, but in a larger space. So you have the same amount of material in a larger space, so it's less dense. So the ball is more dense, and so it sinks, and the boat is less dense, and it floats. Well, that doesn't really satisfy our answer, our previous discussion about buoyant force and floating, right? So we explained that buoyant force is created when an object is put in a fluid, and that fluid pushes back, right? Because it's been pushed out of the way. Well, both of these are in the liquid. Both of these are pushing the liquid out of the way. But because the ball takes up less space, it's pushing away less water. So if it's pushing away less water, then less water is pushing back. And so the ball will sink. While the boat is taking up more space. So it's pushing away more water. So the water can push even harder. And the tinfoil boat will float. So density is a big factor when it comes to how the buoyant force affects an object, right? If the density of an object is larger than the density of the fluid, then the buoyant force cannot keep it up, right? I spelled density wrong there. I'll fix that later. So if the density of the object here is greater than the density of the fluid, so in this case, if the density of the tin ball is greater than the density of the water, so the ball will sink. And if the density of the object is less than the density of the fluid, the buoyant force can keep it up. So again here, even though it's the same mass and it's the same amount of material, the density of the boat is less than the density of the water, so the buoyant force pushes it up. While the density of the ball is greater than the density of the liquid, so the ball will sink. Actual example of density, buoyancy, floating, sinking in action comes from submarines. The only way to make a submarine actually work is to have a good understanding of how buoyancy is applied or can be applied. When we look at a submarine, it's able to float, as we see in this picture, but it's also able to sink. So that must mean that it's able to change its density, because it doesn't change in size, right? It's not changing in size. It's not gaining more. It's not changing in size. It's not getting bigger or smaller, right? So what's making it sink and what's making it float? Well, if you were to look inside a submarine, you would see it has something called ballast tanks. And when the submarine's floating, the ballast tanks are filled with air. And this air makes the submarine less dense, because air is less dense than water. But then the submarine wants to sink. So then the ballast tanks will then suck in more water. And as water is flooded into these ballast tanks, the density of the submarine goes up, because air is less dense than water. So by taking in water, you're making the submarine more dense. And so the submarine will sink. And if it wants to float, it'll pump all that water back out. And as it pumps that water back out, again, it fills it with air from probably tanks, and that decreases the density. And so again, the submarine will rise and float. This video will go over into more detail about that. Displacement, another word you need to know. Displacement is described as when you put an object in water or any other fluid, it will displace or move an amount of fluid equal to the object's volume. That's a lot of words. So, simply put, if you put an object in a liquid, in water, the amount of water that's pushed away from the object you put in is equal to its volume. So let's say this ball had a volume of 1 liter. 1 whole liter. It's a big ball. Okay, well, when I put this ball in the water, 1 liter of water is being pushed away. And what we discussed before is the amount of fluid being pushed away equals the buoyant force, or the buoyancy, right? The more liquid you push away, or the more fluid you push away, the greater your buoyant force. So there's 1 liter's worth of buoyant force pushing on this object. So when you put an object with a container, so for example in this case we have a liquid or a fluid in a graduated cylinder, in the cylinder, and it's at, let's say, 7 milliliters. And I wanted to find out how much volume this object or rock has. Well, when you put an object in a container with liquid, the liquid will rise in the container equal to the volume of the object, just like here. The water, the 1 liter amount of water, is being displaced by this ball. So the water needs to go somewhere. It just doesn't disappear. So in order to find the volume of this rock, we could put it in the liquid or in the fluid. And what will happen is the fluid will rise 2 milliliters. So that means that, based on this rule of displacement, the rock has a volume of 2 milliliters because 2 milliliters was displaced. Just like here with this ball. The ball had a volume of 1 liter. So when you put it in the water, 1 liter of water was displaced or moved away. So, thought problem. You have a crown. You want to find out if it's made out of pure gold or pure silver. All you have are a 0.5 kilogram crown, a block of gold with a mass of 2 kilograms, and a block of silver with a mass of 2 kilograms as well. You also have a bucket with 1 liter of water. How can you prove if the crown is made out of just gold? Right? So this is something we'll talk about in class, and it's actually very, very doable. What you need to do is find the volume of the gold bar. Right? You have 2 kilograms here, you have 2 kilograms here. So you have the mass of the gold bar, you have the mass of the silver bar. So then you want to find its volume, the amount of space it takes up. And using mass over volume, you will get the density of the gold bar, and you will get the density of the silver bar. Well, then you need to find the volume of the crown. Well, the thing about a crown is that it's very hard to calculate its volume. So what you could do is, well, you could put the crown in a bucket of water and find out how much water is pushed out of the bucket. Right? You can find out how much water is pushed out of the bucket. And that would give you the crown's volume, right? That would give you the crown's volume. Well, now you have the mass and the volume, so you can get the density of the crown. And if the density of the crown equals the density of the gold bar, you have a pure gold crown. But if the density of the crown does not equal the density of the gold bar, or maybe even equals the density of the silver bar, then you know that it doesn't have pure gold in it. And that's how you can prove it, by displacing water. Right? Let's say you didn't even know or could measure the volume of the gold bar. So let's say you couldn't even measure the volume of the gold bar. Okay, well you could put the gold bar in water and get its volume. Well, once you have its volume, you can get its density, just like before, mass over volume. Same with the silver bar, same with the crown. And so you didn't even need to measure anything. You just needed to collect water and find out how much volume is taken, how much volume has been displaced. And then you can find the density of the crown, the density of the bars, and then compare them to each other. This was a real example a famous mathematician by the name of Archimedes solved in ancient Greece. He found that if the density of the crown was the same as gold, it had to be made of pure gold. And if it wasn't the same as pure gold, then it would not be the same as pure gold. It would not be made out of pure gold. And so he found out that this crown that he was tasked with finding out whether or not it was made out of pure gold wasn't actually made out of pure gold, because the density of the crown did not equal the density of gold. And this is a very, very important concept, and it's called Archimedes' principle. You need to know this. Archimedes' principle. What it states is the buoyant force, the upward force acting on an object, equals to the weight of the fluid, or the mass of the fluid being displaced by the object. So when we go back here, right, 1 liter of water is being displaced by this ball. That means 1 liter of water is pushing up against the ball. So the buoyant force is equal to the amount of water or fluid being displaced. So the amount of water being displaced by an object is equal to the volume of the object. If the amount of water displaced weighs more than the amount of the object under it, then the object floats. Right? If you displace more water and that water weighs more or has more mass than the object, then the water will be able to push it back harder than it was pushing down, and it can make it float. So an example again here would be a balloon filled with air. The balloon has 1 liter of air in it. And the water balloon also has 1 liter, but this time water, naturally. So this is 1 liter of air and 1 liter of water. Well, first off, you know they both have the same amount of liquid or fluid in it. But which one takes up more space? The balloon with air in it. Right? And we also know from our discussion about the submarine that air is less dense than water. So using what we know, we can determine that the balloon with air will float, while the balloon with water will sink. And that's because air is less dense than water. So the water will be able to push against the balloon and push it back up. In addition, again, we look here, it has 1 liter of air and 1 liter of water. Well, air likes to spread out, like it's a gas, right? Like we talked about in states of matter, right? Gases will spread out. And so now not only is air naturally naturally less dense than water, it's spread out. It takes up more space. So now that mass is spread over a large area, pushing away even more water, causing the balloon to float. Right? So again, Archimedes' principle states that the buoyant force being the upward force acting on an object, is equal to the mass or weight of the fluid being displaced or moved away. Right? So if you spread yourself out, you're pushing more water out of the way, even though you weigh the same, even though you're the same amount of atoms and molecules. Just by the fact that you're spreading out, you're making yourself less dense and pushing away more water, that buoyant force increases and can push you back up. You can do this experiment at a pool. You float by spreading yourself out, by making yourself less dense. And you sink when you curl yourself up into a ball. That's because you're more dense as a ball. You're pushing away less water. While as an open body, spread out, you're pushing away more water. So that force can push against you. And so you float. So how can you measure a fluid density or a liquid density? The tool used is called a hydrometer. Sorry, I said that weird. Right? It's a tool called a hydrometer, and it is used to measure density. It measures how much of the liquid is being displaced based on an amount of mercury in the hydrometer. And that's really it. That's all buoyancy is. It's a little complicated, but you need to know what buoyancy is. You need to at least know what a fluid is. It can be a liquid or gas because they float. You need to know what buoyant force is, the upward force an object feels when in a fluid. You definitely need to know what density is because we talked about this last lesson. It's how much matter is in a given space. You need to know how changing density can affect buoyancy. You need to know how size or space can affect buoyancy or how things float. You need to know displacement. You need to know that when you put an object in a fluid, the amount of liquid or fluid being displaced is equal to the volume of the object, right? Again, if this has a volume of 1 liter, then 1 liter's worth of water has been pushed away. You also need to know Archimedes' principle. You need to know that when you put an object in fluid, the buoyant force acting on that object is equal to the amount of fluid being displaced, right? So the liquid or fluid is going to push back harder if you push away more fluid, which is why boats are so wide, right? If you go back to our first picture here, boats are very, very wide, and their hulls aren't super thick. And if they do have a thick hull, they have to be even wider because they're pushing away more water. And if you push away more water, you increase your buoyant force. And if you increase your buoyant force, you float, or you're more likely to float. So density is very important with buoyancy because it affects the buoyant force, that upward force. Hopefully this made sense. If you have any questions, this is a tricky topic, please come find me in class and we can discuss this further. Thank you for listening.